In this chapter, we will discuss the laboratory stages of porcelain, metal restorations, making, and the composition of the porcelain material and how it is adheres to the metal. The historical of the porcelain was first documented by the Egyptians' finance, where it was coated, clay was coated with a substructure that is ceramic. Then the Chinese developed the porcelain with characteristics that have translucency and hardness. The Europeans attempt to develop the porcelain of a similar quality that was conducted in the 17th century. Then, at the end of the 18th century, this technique was introduced to the dentistry and was started to be used, but not until the mid of the 1950 that it was developed, where the coefficient of the expansion of the porcelain was similar to the dental casting alloy, making it applicable in the clinic, and now it is used in the daily basis. The bonding between the metal and the porcelain is mechanical and chemical. This is achieved by the firing and sand abrasion of the metal before the deposition of the porcelain. Porcelain comes in powder form, and it is mixed with distilled water or an aqueous glycerine liquid, and it is applied as a slurry form to the metal. Then it is fired several times, and we will see the details of this procedure in a bit, where we coat the first layer of the metal with an opaque layer, which is a ceramic layer that will mask the dark metal oxide, and it is the first layer that will ensure the bonding between the porcelain and the metal. Then a body porcelain is added with an translucent incisal porcelain, and then there is a shiny glaze that is maintained from an additional firing step. Here we can see the variation of the thickness that should be maintained for the ceramic and the metal. The metal 1 millimeter is sufficient in the palatal surface, and 1.5 millimeter is recommended for the incisal porcelain edge. 0.3 is sufficient for the metal in the labial surface, and 1.2 millimeter is recommended for the porcelain thickness in the labial surface. The junction between the two materials must be 90 degrees as possible, and its place must be far from the occlusal contacts of the opposing teeth to prevent any failure during function. The minimum thickness of the metal must be preserved during the manufacturing. Less than 0.3 millimeter will lead to distortion during the firing, and it can be measured using the caliper. The margin is usually knife-edged, so the metal is not visible. Before the addition of the porcelain, we do preparation for the metal substructure using the rubber wheel and some tungsten carbide burr, and an airborne abrasion is also used to increase the surface area of adhesion. The next step is to do the oxiding layer, where it is created by placing the metal in the firing tray and inserted it to the furnace. Then the temperature is raised to a specific temperature that will exceed the firing temperature of the porcelain. It is so important, this step, to establish the chemical bond between the metal and the porcelain. How the porcelain is manufactured. It is a blend of quartz and feldspar and other oxides. These materials are heated to high temperatures to form a glassy mass. Then they are cooled rapidly, which causes a glassy mass to fracture into small fragments that are called a fret. This process is repeated several times until we get a desired particle size distribution. Then another crystalline structure that is called the lucite is added to increase the strength of the material. How does it increase it? It is that the thermal coefficient of the glass is lower than the lucite. So when it is exposed to heat, the glass becomes expanded more. When we cool the mixture, it will contract faster, so it will shrink around the lucite particles and encounter it, causing a more rigid mixture that can compensate for the mechanical forces of the occlusion. This manufacturing process does not happen in the laboratory, so the final powder is then used by the dental laboratory after being distributed to the laboratory. Then mixes this powder with water or water-based glycerine. Then some condensation techniques is used to remove any excess water as possible to minimize the steam generation during the drying phase of firing that may cause explosion of the porcelain if it was not baked enough to minimize any moisture that may be present inside the porcelain. Oxides, opacifying oxides can be added to the original porcelain, like titanium oxide or zirconium oxide. Their density is greater than the glass matrix, so that they scatter and reflect the light and effectively mask the color of the alloy substrate. And this is the function of the opaque porcelain, which is the first ceramic coat. Then the body porcelain is added in conjugation with the incisal porcelain. It must be built larger than the intended size because it shrinks during the firing process. The incisal porcelain is usually translucent. So during the manufacturing of the casting alloys, small amounts of base metals that can be oxidized are incorporated. So when we have an alloy that has nickel and cobalt, the chromium is the oxidized that provides the chemical bonding, and when we have titanium casting, it oxidized to fulfill this role. And they are emphasizing the importance of airborne particle aberration with alumina to create surface irregularities that will provide mechanical interlocking with the opaque dental porcelain. These are the possible models of the failure. It can be attributed to the metal oxide layer, or between the metal and the metal itself, or between the porcelain and itself. They are saying that the cohesive fracture with porcelain is greater than the adhesive failure at the titanium porcelain interface. And the reason for the fracture in the porcelain is the inadequate furnace control. Another research about the recycling of inexpensive gold and palladium alloys has found that it did not reduce the bond strength to porcelain. On the contrary, using a recycled conventional nickel chromium has significant reduction in the bond strength of the alloys. These are the types of the metal ceramic porcelain. They can be powders or pastes. Are the porcelain furnaces. After mixing the powder and water following the manufacturer recommendations, we do a substructure. We do the first coat on a substructure that is oxidized. Then we apply another layer. Then we dry it by placing it in front of the furnace. It should be matte white appearance. Then this layer is fired according to the manufacturer's recommendations. It first looks yellow, then when it cools, it gets back to its matte white. Small cracks and fissures are common after the first firing. It can be resolved by application of moisture with a thin mix of opaque material that is condensed into the fissures. Then it is rebaked. Then comes the body application, starting from the neck and going to the incisal edge to compensate for the firing shrinkage that is between 27 to 45% of the mass. We increase the building of the porcelain in the 0.6 in the incisal edge and 0.5 in the mid facial. Then we add the incisal mammalions with the body porcelain that will be covered lately with the translucent porcelain. An index of the incisors can be added to establish an edge position that is uniform. We separate the restoration with a razor before the firing. After it gets out of the firing, we add more porcelain to the contact areas, and the contact area between the porcelain and metal is being seated and adjusted. Then it is baked. After that, we do the complete contouring and shaping using burrs. Then we dry the restoration before it is furnace for 6 to 10 minutes. When it is close to an open muffle, it should not be fired before we get rid of the residual moisture because it will generate steam, and the vapor pressure causes the buildup to explode. After the drying process, we start the firing and we allow the work to cool at room temperature before further handling, and the cooling rate must be followed by the recommendations of the manufacturer because the thermal expansion increases when we do slow cooling. Any defects can be restored using additional porcelain, then we rebake it. But we ensure that it is moistured before the addition of the porcelain. We must be aware about the excessive number of firing will lead to loss of translucency and decrease in the restoration's fracture resistance. Internal stains can be added to mimic the natural effect. And translucent powder can be used to enhance the incisal translucency, like this. You can see the translucency in here. As for the glazing, there is what is called an auto glazing that can be achieved by raising the temperature of the paint, but what is called an overglazing, when we use a separate mix of powder and liquid and we apply a layer, then we fire it, is not recommended because they include low fusion to porcelain. Now let's know the pressed metal technique. After we oxidize the metal and adding the opaque and firing it, we do normal waxing. Then we invest it and add the block of the porcelain that is impressed from the pressure to get it from the block to reach the metal and incorporate to it. Then we do the incisal shaping using burrs and add an covering incisal porcelain with special powders to get this final realistic look. Final pictures of the steps. Here is the sprue attached to the wax, and this is the investing, and this is the covering of the surface. This is the press ingot, and this is after the pressing and smoothing, and by adding stains to get this realistic result. Thanks very much. Salam.